Okay, so we're going to continue on in this chapter about molecular absorption. And to do this, I want to first explain a little bit more about the types of transitions and what's going on in molecules when they absorb light. What exactly is one of these electronic transitions that we're talking about? And to do this, I'm going to review something that you remember from general chemistry. Way back when, General Chemistry 1, you learned about atomic line spectra. And what this dealt with was properties of atoms. Specifically, it said that at the center of the atom was the nucleus, and then you drew these little concentric orbitals, and you gave them numbers, n equals 1, 2, 3, 4, so on, and so forth, right? Now, each of these circles or orbitals were basically locations where you could assign electrons to it in this early Bohr model, okay? And the electron could exist in n equals 1, or maybe n equals 2, n equals 3. And the electron could even move between these levels, potentially. But the main idea was that the further away from the nucleus you get, the higher the energy of this Bohr orbit. So because of that, an electron in atoms, such as the one depicted on the left, would tend to wish to reside in the lowest energy orbital, way down the n equals 1. That's closest to the nucleus, right? But with that said, we can move that electron between orbitals, but that process wasn't free, right? So maybe the electron starts out in the n equals 1. We're going to call that actually the ground state, the lowest energy state, okay? So the electron starts out in n equals 1. Now I can move it up to maybe n equals 2. Maybe I can even move it all the way up to n equals 3. But since the higher numbered orbitals are higher energy, there is an energy gap, delta E, that I needed to bridge. Keep in mind that that delta E could be bridged by a photon's energy. If the energy of the photon is given by h nu was exactly right to bridge that energy gap, that atom could absorb that radiation, that photon of light energy, and the electron could be promoted to the higher level through a process called absorption. In this case, atomic absorption. Now, absorption is always exceedingly fast. It's believed to occur somewhere around the time scale of 10 to the minus 15th seconds. Okay, it's a very, very, very fast event. But nonetheless, these electrons could move between these allowed Bohr orbits. But electrons couldn't exist between Bohr orbits. They had to be in one or the other. So if we move from a lower one to a higher one, okay, that is absorption. And you could also do the reverse process where you move from a higher back down to a lower. And that occurs, that's emission of light. And there, a photon of a specific energy would be given off to the outside world. Okay, so the electrons could move around. And this is a kind of a useful discussion to have because, as it turns out, there are some differences in molecules, but there are also some similarities. So let's talk about molecular absorption now. Well, at the tail end of General Chemistry 1, you started to talk about molecular orbitals or molecular orbital theory. And you learned about molecular orbitals for very simple molecules like H2 or HCl, things like that, okay? Just basically two atom molecules. Well, what's the difference? Well, molecular orbitals are orbitals which belong to a molecule as a whole. But the thing is that they kind of function similarly to atomic orbitals in the way we place electrons into them. Okay, so an electron in a molecular orbital, and these are depicted over here on the right, by the way, okay? Maybe it resides in this bottom boldface line. We're going to call that the ground state. Similar terminology. It's basically the lowest energy state that our electron can be in. So we're going to place that electron in this ground state, which is again a molecular orbital. It belongs to the molecule as a whole. And if we're going to do an electronic transition, what we're going to do is we're going to take that electron, which is in this molecular orbital. Sometimes it's called the highest energy occupied molecular orbital, or HOMO. And we're going to move it. We're going to move it from this ground state where it typically resides because it's the most energetically favorable. And we're going to place it into a different molecular orbital. maybe we bring it all the way up to here. Now, if I bridge the gap from the E0 to the E1 level, which are again are two different allowed electronic levels in this molecule, what I've done is performed an electronic transition. Think of it as moving the electron from one molecular orbital to another type of molecular orbital. That molecular orbital is still allowed, but it's higher in energy. And you guessed it, there's an energy gap between these. And just like the case of atomic orbitals, I'm going to have to pay that energy price in the form of a photon. So that molecule is going to have to absorb a photon of light energy to bridge the energy gap, to go up in energy, because as we move higher in this figure, we're at higher and higher and higher energies. Okay? Again, that event going from a lower level to an upper level is called absorption of light. Okay? Now, what's different about molecular absorption compared to atomic absorption? Well, in molecular absorption, we've got collections of atoms bonded together, don't we? Chemically bonded together. Now, what's the significance of that? Well, one of the major significances within each of these electronic levels, which are E0, E1, E2 here, okay? These are all electronic levels. Now, within each of these electronic levels, or these different molecular orbitals, there are ever so slightly different allowed vibrational energy levels. And you see these little lines that are not bold-faced, like labeled 1, 2, 3, 4? That is what we are depicting in those lines. These are vibrational energy levels. So in addition to going just down here from the ground state and performing an electronic transition, I could go from the ground state up to an excited state and end up in the 0 vibrational level. Or I can end up from the ground state and go up to the n equals 1 vibrational level, or the 2 vibrational level, or 3 or 4, or so on, okay? Now these vibrational levels are very, very, very closely spaced typically, okay, in energy. They don't vary very much. And what they really correspond to is different allowed vibrational modes of the molecule, if you want to think about it that way. And notice that down here, if you were really perceptive, we went from the ground state up to the first vibrational level, second, and so on. There, you would actually be doing purely vibrational spectroscopy with no electronic component. That would be like what you do in IR absorption spectroscopy. In infrared spectroscopy, the photons are too not energetic enough to bridge the larger energy gap between molecular orbitals. So you cannot do an electronic transition with infrared photons, but you can do purely vibrational transitions, and that's what you would be doing down here at the bottom left-hand corner. But nonetheless, because there are these allowed vibrational levels, we're able to have multiple options during our absorption event to go into. Now, you notice that the arrows then are of varying different lengths. So that first arrow would be about that big. And remember, these corresponds to energy gaps. So the second arrow will be a little bit bigger, wouldn't it? Because I need a little bit more energy to get to that n equals 1 vibrational level. That third arrow will be all the way up to the 2. That arrow will be even bigger yet. If you get up to 4, it's going to cost you even more energy, right? So not only do you have to bridge the energy gap between the molecular orbitals, the electronic transition, you also have to bridge that energy gap to higher vibrational levels as well. And this is a big difference, okay, between molecules and atoms. Atoms do not have these vibrational levels because they don't have bonds between them holding them together. You can only have these vibrational levels if you've got molecules with bonds, okay? Now, what's the significance of this? Well, one of the major significance, points of significance here is that multiple absorption options are possible with about the same energy, okay? About the same energy. And that's going to be very significant, okay? Because when we talked about line spectra, and actually I should go back to that slide. When we talked about line spectra for atoms, their absorption or emission spectra look like this. Now what this is a plot of wavelength, kind of a proxy for energy, right? Because we know frequency is proportional to energy, wavelength is inversely proportional. So down here will be the highest energy, and over here would be the low energy end of this particular figure. But it's the visible emission or absorption spectrum for several different elements. And if you were to look at what this would look like, what you'd find is a series of lines that look like this. Now, these are all absorption or emission features at exceedingly specific wavelengths. Very, very, very specific wavelengths. And each element has its own characteristic pattern, but notice that each element has a very, very narrow emission or absorption line at a very, very, very specific wavelength, very, very spectrally pure colors, okay? Now let's compare and contrast this case with what we see for molecules. This is a molecular absorption spectrum, very similar diagram, except it's much broader. We'll talk about that in a second, but this is our wavelength. So over here is our low energy and our higher energy here, okay? So wavelength's kind of a proxy for photon energy, right? And in this case, we're taking a spectrum of that molecule right there. It's this 1, 2, 4, 5 tetrazine. The actual molecule itself is not super important. But what I want you to see is the differences between this absorption spectrum, plot of absorbance versus wavelength for a molecule compared to an atom. Now remember, we said for a molecule, there's all these other vibrational levels that we can populate during an electronic transition or an absorption event. What's the consequence of that? Okay, well, if you think about it back from that previous figure, there was a series of different options where we can go from the ground state up to an excited state, an excited electronic level. But because all those different vibrational levels existed in molecules, there was a series of absorption options of ever so slightly different energy. And that's really crucial, because what that means for us is that the absorption event for a particular electronic transition will not occur at a very specific frequency, but will occur over a small range of frequencies or wavelengths because of the vibrational levels. So if we made a plot of absorbance versus wavelength for a vapor phase absorption for this molecule, we might see something like what's up here at the top, okay? There's a series of peaks, right? Sort of spread out in wavelength over maybe 50, 75, 80 nanometers. So they're all slightly different energy. And each one of these then correspond to an electronic transition to different vibrational levels or between different vibrational levels. Okay, so one of the major points that I'm trying to make here in this video is that for molecular absorption spectra, the spectral features are much, much, much wider than what we observe for atomic spectra, not even close. For atoms, line widths of the spectral purity of the light that you see during emission or absorption might be less than 1/100th of 1 nanometer. But for molecules, our absorption features tend to be 50, 60, 80, 100 nanometers in width. And that's a big, big, big difference, as we'll see. And that originates because of the richness or the large number of possible levels that we can absorb into because of these vibrational levels. And there's even what's called rotational levels, and that even blurs things out even more. Now, another thing to actually look at on this particular slide is differences observed between the vapor phase spectra for the same molecule and the molecule in a hexane solvent and aqueous solution. So the top is, this is a gas phase spectrum, and we see all this fine structure, all these nice little closely spaced peaks. But what happens if we take that molecule and put it into a solvent? So the first solvent we're going to put it into is hexane. Hexane, of course, is a non-polar solvent, and then we're going to take the same molecule, put it into an aqueous solution. Let's take a look at what the differences in the spectra look like. So in hexane, the one here in the middle, the first thing I notice is that I still kind of see like an averaged out vapor phase spectra. If you want to talk about that in that term, right? It's kind of averaged out. So I still see similar, different peaks, if you will. But they're just kind of blurred, aren't they? And then when I look at the aqueous solution, gosh, I even move all that. I just get a big old hump there. So yeah, it's absorbing some light, but I don't see any discrete individual peaks at certain wavelengths anymore at all. It's been completely blurred out. And this is actually normally encountered when we start taking our molecules which absorb light and we start putting them into different solvents. And this effect is worse in polar solvents. This blurring is worse in polar solvents. And the reason really why this occurs is that when you take your analyte molecule, which absorbs light, and you place it into a solution, condensed phase, a liquid, molecules start getting much closer together in the condensed phase, okay? And they can start to interact through these intermolecular forces that we've talked about, okay, back in general chemistry. And that has a net tendency of basically blurring out the spectra. So no longer can we see the individual peaks of flat structure shown up on top. Instead, we just get a blurred out spectrum. So while an atomic absorption, if I plot absorption versus wavelength for an atom, gives you these very specific wavelengths. These are all lines meant to be, on our scale, essentially infinitely narrow. And they're not in truth infinitely narrow, as we'll learn in the next chapter, but really narrow spectra for atoms. Each individual wavelength is very specific. It almost serves like a fingerprint for the atom in question. But for molecules, you tend to get this blurred out spectrum, especially in the condensed phase and liquids. And the spectral features might be 50 to 100 nanometers in width, maybe even wider than that. So the atom's spectral half width might be 0.01 nanometers. Not comparable at all. Okay, it's much more narrow. And that's one thing I wanted to take you from this discussion. So there's a couple of reasons why that is. One of them we actually hit on this slide. The large number of potential vibrational and rotational levels help to ever so slightly spread out the distribution of possible absorption wavelengths and frequencies. And the second reason why our spectra are blurred or spread has to do with placing the molecules into a solvent. It has to blur out the spectra even more, okay? So molecular transitions then. Well, we've learned in that previous slide, that energy level diagram, that there's a large number of possibilities because of all these vibrational states. But we're actually going to kind of take a step back now and look at groupings of common types of transitions. And we're going to kind of give them names, basically. Now, we studied these electronic transitions involve taking an electron and moving it between allowed molecular orbitals. And when you were studying those molecular orbitals back in Gen Chem, you learned there's a couple different types of these molecular orbitals, okay? One of them was called the sigma, and the other major type is called the pi. And how these are different is how atomic orbitals overlap to form them, okay? So the sigma is shown here. And if you have what I like to call end-on-end overlap or overlap of spheres, like if you consider two spherical s orbitals and you overlap those, you're going to end up with a sigma type interaction. You could also have a sigma type interaction from the overlap of atomic p type orbitals. And those are the figure 8 shape. If they overlap like that, that is a sigma type interaction, end-on-end overlap. Now remember, if you take two atomic orbitals to make two molecular orbitals, whether they're sigma or pi, you basically have to make the same number of molecular orbitals as you used atomic orbitals. So in the case of sigma, what you end up making is a sigma bonding molecular orbital and also a sigma star anti-bonding molecular orbital. And the idea there is whether or not the orbitals combine in phase or out of phase, we'll say. So these are two of our possibilities. Now, the sigma bonding tends to be lowest in energy, and the anti-bonding sigma is highest in energy. So we put those on the extremes of an energy axis here. Now, what are some other options then? Well, some other options for the molecular orbitals which can form in bonds are pi type molecular orbitals. Now, these would result from what I like to call side-on-side overlap. Consider a p orbital that's dumbbell shaped, getting close to a p orbital on a second atom, which is also dumbbell shaped. Nucleus at the center. Now, because you bring these p orbitals close together, they can start to overlap, form a molecular orbital. They can overlap in phase, they can overlap out of phase. And if they do, they will make what's known as the pi bonding orbital or the pi star anti-bonding orbital. You guessed it, the bonding one is of lower energy, the anti-bonding one is of higher energy. Now our cartoon energy diagram over here on the right, you can draw those in. Now, there are other electrons typically in structures of molecules that we haven't talked about. You know, sometimes you assign those lone pairs, don't you, to certain atoms. And those lone pairs, they're kind of like our model is they exist, you know, on that atom by itself. The lone pairs are not necessarily involved in a certain bond, are they? So we're going to call those the N electrons, or non-bonding. Put them somewhere in the center here in terms of their energy, okay? So what are we going to do with all these possible different molecular orbitals and electrons? Well, we can take electrons which are present in each of these orbital types and move them around. Now if you're going to fill in one of these diagrams for a molecule, you basically like count up all the electrons and then start assigning them to the lowest molecular orbital until you fill it up, and then you'd move, you know, up in energy just like you would for atoms, right? From lowest energy to highest energy. So we'd end up with, you know, electrons in, you know, different orbitals here. You might have a couple like this, maybe some like this, maybe up here, and even the non-bonding. And I'm using these arrows to denote electrons, of course, right? So now the fun with the spectroscopy starts, because we can move these electrons around, perhaps. So let's just say we take a sigma electron, one of them here, and move it all the way up to sigma star. Sigma to sigma star transition, right? Well, that type of transition, gosh, that's going to require me a ton of energy. That's the largest energy gap of any of these, right? Huge amount of energy is required to do that on a molecular level, right? So because of that, we're going to need energetic photons. We're going to need things down way down low in the UV, or maybe even the X-ray range. So because of that, chemists, they don't usually do electronic spectroscopy on this type of transition for a couple of reasons. One is you need very energetic rays, down even sub-UV range, into the X-ray range. And it's hard to make that light, it's hard to use it, it's dangerous to us, right? So that's one reason that we don't usually use that sigma to sigma star transition. Another reason is it turns out that like almost everything absorbs this type of radiation effectively, even gases in the room air. So oftentimes you have to go to extreme experimental extents to even make this light and transmit it through the room, because gosh, everything will absorb it. And as it turns out, like this sigma to sigma star range, if you're promoting an electron from sigma to sigma star, you're basically breaking a sigma bond. There's a very good chance you're doing that. And your molecule may just fall apart, right? So we don't use that one all that much, but nonetheless, it's a possibility. There are other types of transitions that chemists might use. For instance, there's N to sigma star, or maybe N to pi star. And this is where you take an electron, which is in one of those non-bonding orbitals or lone pairs, and you promote that electron up to either a sigma star or a pi star orbital. So maybe this type of transition or alternatively that, okay? So if you're going to do this type of transition, you're probably going to be either needing a UV photon for the larger gap or UV and maybe even into the visible a little bit, depending on the actual molecule and its energetic structure. But nonetheless, this type of transition is a significantly smaller energy gap than the sigma to sigma star. And because of that, it's a bit more spectroscopically useful. And then lastly, we have the pi to pi star transition. This is where you go from the pi bonding up to the pi star anti-bonding. Again, UV and visible photons can be used for this type of transition. Now, if you are doing a pi to pi star, it turns out it's kind of a special type of transition. Intensities for absorption or molar absorptivity for this type of transition are unusually high. So it's a strong absorption event, as it turns out, okay? So these are all the different options in terms of transitions from between molecular orbitals. And you see this lingo thrown around quite a bit. So I just wanted to kind of mention what that was all about. So it's not a big mystery to you. We're going to tend to show like cartoonish pictures, excuse me, when we're talking about these molecular absorptions, maybe pi to pi star, N to pi star, those types of, it's almost cartoonish in a way. I mean, it describes the molecular absorption, but it does not give you specific information about the specific molecular orbitals involved in the molecule that the electrons are moving between. And in fact, if you have that very specific information available to you, you could actually predict the electronic structure of the molecule. You could predict what frequency or wavelength that molecule will absorb. But nonetheless, throwing around this lingo is sometimes useful, okay? All right, now because of these specific molecular orbital cases that we talked about on the previous slide, chemists can draw generalizations about absorption features in different molecules. And what I mean by that is different molecules that have similar functional groups, because they have similar functional groups with similar atoms bonded together in similar ways, they might exhibit similar absorption features, and in fact, they do. So certain arrangements or functional groups within molecules that give rise to absorption bands, we're going to call them chromophores, okay? Chromophores, it's a special name. It's a certain absorption feature. It's because of a certain functional group. Now, this is very similar to infrared spectroscopy that you learned about in organic chemistry, where you use certain IR absorption features to, basically confirm the presence of a certain functional group. It's a similar idea, but it turns out that chemists really never use these chromophores for structural identification or structural verification. Not in the UV invisible. Maybe in the IR, but not in the UV visible, okay? And the reason why is because these spectral features for molecules tend to be very, very broad. And there are a large number of these chromophoric groups that would more or less overlap with one another spectrally. In other words, they absorb at the same wavelength. So if that's the case, there's really no selective basis for trying to look at a UV absorption spectrum and assigning functional groups. Chemists just don't do that because the absorption features, they overlap way too much and they're way too broad to get any useful information. However, you may be able to kind of go the opposite direction, okay? Say you had some kind of structure, okay? Like maybe the structure I'll draw here on the slide. Maybe you could take that structure and you'd like to have the ability to predict what wavelengths of light maybe it will absorb. Because you'd like to detect it with an absorbance detector, and it'd be great if you can kind of predict what wavelength that would absorb. Now, I'm not going to confirm that that structure is present by an absorption feature, but I can go the other way. I could say, oh, here's my structure. Well, it's an arrow. Here's my structure. What wavelengths will it absorb? So that's what this table is useful for, this table of chromophores. So what it is it's just a listing of different functional groups from alkanes all the way down to nitrate group, okay? And each of those groups has sort of a typical lambda max, or typical wavelength of maximal absorption. These are all in nanometers, of course, which is the typical unit of measure for UV-G's wavelengths. So these are basically the wavelengths of maximal absorption. And again, this is not precise. There's going to be some broadening in these features. It's going to drift one way or the other. That's why they all kind of overlap. But alkanes might be expected to absorb down below 150, and that's because you really need to do that sigma to sigma star absorption down there. So we're not going to use that feature much. But other functional groups have spectroscopically more useful absorption features between 200 and 300 nanometers. It's still down the ultraviolet, but I'll tell you what, this range above 200 nanometers is a lot more friendly and more easily accessible experimentally. So each of these groups have a particular wavelength of absorption. These are called chromophores. All right, so I'm going to end this video here, and when we get to the next video, we're going to talk about instrumentation.